Hello, good morning, good evening, good afternoon, everybody, wherever you might be. So we start our spring semester, and our first speaker is Yang Liu from SISSA. Hopefully, in a few months, he will be from IMPAN. It's quite likely. And the title is Cyclic Structure Behind the Modular Gaussian Curvature. The Zoom is yours, the floor is yours, take it away.
First of all, thanks so much for the invitation. So to have this great opportunity to present some recent progress. So in this project of this modular Gaussian curvature, so on non-commutative torus. So the big picture of this project is somehow to explore like a develop like a Riemannian geometry, right? So in purely this language, this function in the language of a functional analysis. So here is the outlines of my talk. So I will first of all I will review some key takeaways for this the definition of this modular curvature. So the main focus is to study some sort of the variational calculus behind behind this curvature computation. So I think that the main result is sort of a cyclic module structure in here. So I put a double quote in here because so I do not have a full cyclic module. Some axioms should be is modified. So at the end, so if I have time, so I will give some applications or some quick computations to show that how this cyclic sort of a cyclic structure help to assist in the computation here. So okay, so first of all, let's go to our favorite example in non-commutative geometry, which is just a non-commutative tori. So here is I make a list of some basic notations of differential calculus on the smooth non-commutative tori. So let me try to get away with this. So for integration, so we have a sort of a canonical trace, which is a tracial functional on this algebra of smooth coordinate functions. So and then it gives rise to following this standard G and S construction. So we have an inner product, so that once you and then the Hilbert space is simply the L2 completions. So with respect to such a inner product. So, and for differentiations, so we have this from 1 to m is the dimension. So, and basic derivations, so they simply play the role of I times this partial derivatives. So, and then in particular, so the flat Laplacians, so can be written as just this partial x1 square plus some partial x and m squares in here. So this is basic notations for the differential calculus, like pretty much identical to what happens on the torus. So here, so this delta represents a flat metric, the usual Euclidean metric. So to obtain a curved matrix, so we can consider sort of a conformal change of metric. So we start with self-adjoint elements, which whose exponential is the conformal factor. So I will call H the log conformal factor. So and then first off, then you can change the volume form. So I think I missed the. So here should be phi 0. So the new volume form is kind of a rescaling of the flat one with phi 0. And then, so we can try to figure out the new Laplacian following the model of this double Laplacian. So So in dimension 2, so it has this a degree 0 part which acting on functions. This Laplacian has the following simple form. So you just put two copies of the Weil factor on this flat Laplacian. These operators gonna represent sort of the Riemannian metric, and then how to extrapolate like local invariance, or like in particular the notion of curvature out of this metric. So the model we use is the standard results on the spectral geometry on Riemannian manifolds. Excuse me. So let me clear this. So I think that the main tool is like we shall consider this heat trace asymptotic expansion of the associated heat operator, which is e to the minus t of this Laplacian. So since we're on a purely functional analytic setting, so we don't have the notion of Schwarz kernel for differential operators. What we do here is we insert a little bit this arbitrary element A, and we view this trace as a functional in this A, so that in particular each heat coefficient so going to be a functional. So and then in particular, so in the process of proof this asymptotic expansion, so one can show that this abstract functional is absolutely continuous with respect to this phi 0. So you can think of phi 0 is just like a integration against the flat volume form. So and then it has a as a density, so which is an element in this smooth algebra. So the main result is on closed manifolds. So we have a classical result. So I mean this even before like a Gilkey's computation, I think we know that this the second coefficient, the first coefficient is really recover the volume, and the second coefficient is proportional up to a universal constant. So we recover the scalar curvature function associated to this metric in here. So this gives a sort of a model like using purely sort of a functional analytic language, right, to capture the scalar curvature. So by the standard Mellin transform argument, so it is like a folklore that so this small time asymptotic expansion of the heat trace so corresponds to this a meromorphic continuation of the spectral zeta function associated to the Laplacian. So in particular, so in dimension 2, let's focus on dimension 2. So and then the second coefficient, the A2 here, so corresponds to the point, the value 0 of the zeta function. So the very first result of this project is the Gauss-Bernet theorem. So first proved by Kohn and Trekov, and then there's another version is given by Fadizat and Kaukali. So this so in our language, in this operator theoretical language, so the statement is like so you consider this the value at zeta function is a functional in H, and this function is a constant function. So this is the sort of a fancy way to rephrase this integration of the scalar curvature. So that's the first step is kind of a you only concerns the integration of the scalar curvature. So of course, and then the full A2 term, so the the full formula of this R2 shall carry like a more information. So this was first achieved in a Kolmos-Kovic's James paper. So and then the computation was also independently carried out by Fatizad and Kaukali. So and then of course the two results agree. So and then later there are many other contributions from this list of authors. So I will apologize if I'm missing any names. So apologize for my ignorance. So here is the sort of a brief literature of this project. So okay, so I'm from here. So we have sort of a model to define this the scalar curvature as for example as the second coefficients in this small small time heat trace asymptotic. So actually, so I would like to emphasize a more delicate definition, so mentioned in Kolmos-Kovic's paper. So to make use of this variation. So notice that the first step. So we look at this zeta function at 0. So we have a constant function, right? So and then what to do next? And then the next step is that so once you have a constant function, then naturally we can look at the derivative of this function, the first derivative of this function at 0. So this is the Ray-Singer determinant. So following the model on closed on Riemann surface, this is a famous paper of Oskar, Philipp, and Sonak. So this they introduced this sort of normalized functional. Is like the main part is this Ray-Singer determinant with a modification. It's like it's kind of like a normalization divided by we call that in the Yamabe functional, right? So you have to usually divide it by the volume form so that it does not change once when you're rescaling the metric. So and then you take log, this divided becomes this additive in this way. So what's the nice thing about this functional? So this I think it's been shown in this paper that when you consider this a gradient flow of this functional, then we recover the Ricci flow, I think, on Riemann surface. So and then yes, this paper of Kohn and Moscovici somehow implements most of these discussions in this paper onto the non-commutative tutorials. So okay, so now we have a geometric functional. So basically derived from the Ray-Singer determinant of this spectral zeta function. So in here, the more details about this gradient flow in our setting. So it's given as follows. So we consider the following variational problems. So the domain of our functional is all the self-adjoint elements in our algebra, the smooth functions on non-commutative. So then we introduce a small perturbation along any other arbitrary self-adjoint direction, and then we consider this variational taking derivative in this parameter epsilon here. So we define the functional gradient in the following way. So we can differentiate this functional. So the result will be a linear functional in A. So once this A is again absolutely continuous with respect to phi 0, and then we if we can prove that, and then we call this whatever the Rodin-Nikodym derivative, which is an element in this algebra. So we call this a functional gradient. So by sort of this exact analogy, so into the commutative case, we can sort of define these functional gradients as the modular Gaussian curvature. So in our case, it's so this gradient is very close to this this R2 here. So but I think the results they do not differ very much, but I think so this variation adds to sort of make this somehow sort of a deeper notion. I think it's okay. So after after some heavy computations, so one can obtain this explicit formula of this functional OPS functional and the gradients in terms of this log Weil factor H. So here the new ingredients. So first of all, let's look at expressions like this and this. So this is so it's saying that this so this is sort of so compared to the classical case, this simply saying that this I will call it differential expression is involved like only up to the second derivative in H, right? So you have a Laplacian and a delta is like it. So the new gradients is this T of this nabla and a K and H. So I will call them rearrangement operators. So this nabla or like this triangle, the upside down triangle is the basically is the commutator with respect to H. So it called the modular derivations the modular derivation because it is the infinitesimal generator of so of the one parameter group of automorphisms attached to this to the new to this new volume form phi. So
sorry, what is T then? This is explicit.
So yes, I will explain. So T, K, and H, there are some very concrete functions. So first off, so at this stage, so you can think of T maybe as polynomials and the K and H there as polynomials. So and so later I will give you the more detailed the definition. So in here 1 and 2 means that I only, so you think of this as polynomials like I will use some formal variables like a sum of like a x1, x2, and then the x1 will act in on here and x2 will act in on here. So probably I will, so yes, these are the new ingredients in this this modular curvature. It appears due to the fact that the derivative of H and itself do not commute. So I can do some, I should do some very quick computations here. So for example, like if you take the derivative delta J of H squared, so and then you can apply the Leibniz property. So you have H times delta J of H and plus delta J of H and H. So, but now, so you cannot combine in this into 2 times this. So another, so basically, so this then I use this this commutator somehow to move this H in front, to move this H in front. So another example, which is somehow a more sophisticated, is the Duhamel formula. So let me do some very quick computation. So here, so I find some. So so we know that this is, so say I want to compute the derivative of some e to the h. So this is or like this e to the h plus some delta of h has this expansion at this e to the h plus 0 to 1. So e to the, this is e to the s of h. This is delta of h, e to the 1 minus s of h, and the s. So and plus some higher order terms. So and then we can factor out this this one here. So you have so e to the h plus e to the h times this 0 to 1. So this e to the h s of h delta of h e to the minus s of h ds. So this is we see that we have a conjugation here. So this so I can write like a e to the this modular derivation times delta of h. Here is an s. So this integrate from 0 to 1 ds. So and then you can, because this does not depend on s, you can move it out. So I will write it as this 0 to 1 e to the s of nabla. So ds apply on this delta of h. So and then this is exact. So once you integrate in s, so you have this e to the, so apply on delta of s. So you have this kind of functions. So the underlying function is like e to the x minus 1 over x, right? So this is well known as the Duhamel formula. So then you have this such a function, such a rearrangement operator floating around. So they consist of so-called this quantum part of this modular curvature. So and then once you get into the second derivative, so then you are, because I only did the first derivative, like if you differentiate more, and then you will see you have something like a product of this delta of h, then you need a sort of functions of two variables. So in the classical case, this k and h will be just some numbers, right? So in a classical case, for example, like on the, so on the usual two torus. So after this this conformal change of metric, I think the new scalar curvature, this delta of g of prime, I think it's equal to the Laplacian of h. I think this is very simple, like on the two torus case. And for higher dimensional, like you have a delta, the difference of the two scalar curvature. So it's like it's something times the Laplacian of h plus something times the lambda j of h, lambda j of h. so some Gij, like remind me. So and I think so Kolmogorkovich's these papers, I think they give some many like explicit computations to show that these functions k and h, this sort of a modular part of this curvature, so somehow has huge influence on geometry. So okay, so after explaining the sort of the meaning of these new ingredients of the modular curvature, so I've arrived at my sort of the starting point of my story is this following simple functional relations between these k and h. So what's important about these rearrangement operators is the underlying functions behind that. So like I will call them like the symbol of the rearrangement operators. I think that these underlying functions captures most of the important information in here. So the result of a Kolmogorkovich is that we have a very following simple functional relations between this k and h. So conceptually, because this k is defined as a sort of a, this expression sort of as the Euler-Lagrangian functions or Euler-Lagrangian equation of such functional, right? So it's not an arbitrary like combinations of the two terms. So it's the Euler-Lagrangian equation. So therefore we naturally expect that there are some relations between this k and h. So here it is. So any questions so far? And then once you then yes, so I basically my whole talk is about okay, what are the sort of the mathematical structures behind these relations, right? Okay, so here is a few list of some of probably observations you can grab from this explicit formula. So first of all, so if you look at the three terms on the right-hand side, so you see this divided difference shall play a crucial role in each term. So this observation, I think, is due to Lesch. I think I learned a lot from this his paper of the divided difference in noncommutative geometry. I think his paper has a sort of a huge influence on all this progress I'm going to report later. So the first observation is the divided difference in here, and then if you look at this divided difference, right, you're setting the limits when x1 approaches x2, so you get the derivative. So there are some potentially kind of differential relations behind. So and then the other observations which could be seen is that so if you look at these arguments between these three terms, there are potentially some cyclic permutations behind that. So then as you expect from my title of the talk, so this cyclic permutation, so it's kind of, it plays exactly the role of this cyclic group in the cyclic category. So that's some quick some preview of the main result. So okay, so also let me tell you a little journey about my understanding about this personal understanding about this computation. So the first step is I try to reproduce some Konner and Moscovich's computation on other examples, like so on this I did this on the so-called theta deformed the Riemannian manifolds, and then I think Fazada he did the same sort of a similar computations on non-commutative 4 tori. So I think we arrived at the same result, and this the sort of a last organized functional relations. That's the first step. I try to just mimic the computation in Commons curvature and in sort of in higher dimensional examples. So I mean, once then I repeat this computation set several times, then I realized that I can this sum indeed can be like there are cancellations behind. It can be simplified to a sort of a three-term relations, like in this formula. So and then I think so. I consider very lucky. I think it was in 2019, like probably a few months before the pandemic. I had a visit with Alan, and I shared this progress with him. And then I think the very first remark, so he pointed out that so I explained the cancellations behind it. He pointed out that this is exactly the relations in the axioms of his cyclic category. So basically, so I think my main result should be somehow a more comprehensive interpretation of his vision on this subject. So okay, so before stating my results, so I will want to talk about another motivation. So why? So it's about the A2 term. So and this 2 and 4 refers to the index J here. So the A2 and A4. So and also in this case, 2 and 4 is also reflects exactly the derivative involved. So A2 term involved exactly the second derivative of the metric, and A4 term so involved up to the fourth derivative of the metric. So and then one expect that the computation will be like a much more complicated. So here is the table of contents of this of their paper. So something I want to highlight. So in here So still, for the A2 term, we can sort of reproduce some similar. So they still exist, these functional relations from this variational computation. And also there is an action of the cyclic groups, as I mentioned as 2 slides ago, like about this observation. And okay, so the next slide is going to be so here is the full A4 term, so obtained in the computation. Sorry, I forgot to mention it. It's this Kohn and Fatizad. So this Alan and Fazad. So as from these expressions, even though it's long, but so for example, like so it consists of the fourth derivative, right? So you have 2 here, you have 2 here. L is just the H as before, the log biofactor. So and then basically it's a differential expression, because since we're in this operator theoretical setting, so and then we have to deal with this rearrangement operators as coefficients. So by the way, another remark is that so this rearrangement operator, for example, is not necessary. So for my understanding, so this is the optimal way to organize the terms. If you don't use this rearrangement, probably you have many terms. It's like you have a polynomial, like 10 terms. So and then if you don't view this polynomial as a function, you have to write down 10 terms. But then you can group everything as all, it's kind of a compress all these ansatz of 10 terms as a function, as a polynomial. I think that's a sort of a main motivations why we needed this rearrangement operators as coefficients. I think it's the best way to present the results, so that the formula has sort of the minimal length. So any questions so far about these notations.
So you say you can basically do better than this result? Is that what you're saying? Or is this the result that is better than the previous one?
So this, I didn't, you mean the A2 term?
It says right here A4 equals, and then it's it seems like not very long for what I would expect.
Oh,
So,
yeah. So I think what's long is those functions. I mean, yes, the full formula is yes. So we can yes, it's not still we can process as a human mind, right? It's not that long, but I think what's complicated are the functions, this k1 to until k20, I think so. Yes,
they can be simplified because there's still minus signs in these functions k, right?
So you mean
I'm just asking what are you saying about this formula that you can, I mean, that you can do better than these k?
Oh yes, my motivation is like trying to give some simplifications behind this formula, but so far I'm not able to, I've not yet to reach the stage of produce like explicit simplifications. But yes, that I'm saying that this is the motivation that so I will somehow to like improve some computational tools so that we can have some potentially simplifications of this.
I see. Thanks.
Yes, what's complicated is somehow the functions behind. So they can be explicit computed, but so it turned out to be quite lengthy. So but okay, so this is the explicit formula for the A4 term, but here is I will try to enlarge. So here is a part of the functional relations for behind this variational computation. So
was this formula for the A4 term?
yes, this is a
was a computer used? How was a computer used to get this formula?
So I think it's so this formula is so it's a similar way. So you have to compute some variations like that. You compute similarly, so some gradient like that. So it's a.
Well, I'm just asking if a computer was used.
Oh yeah. Of course, this is the result is generated by the computer. Yes.
I see.
Yes. So
hi, and all these are polynomials k1 to k20.
No. They are k1. So they are. So you see that you have exponentials in there, right? This is e to the s. So okay. They call this exponential like polynomials, I think so.
Yeah, I mean, I think it's important to know indeed what type of functions you get, but you get functions which are indeed, exponentials with very neat type of exponents, products and so on, and also polynomials. But the same type of functions are very common in transcendence theory.
Yes.
So, yeah.
So, yes. So roughly, like we have two difficulties, right? So when you look at these computations, first of all, is to sort of find the best way to represent those functions like k1 to k20. So this is but this is not my main object today. So, but it's a very challenging task. That's the first part. And the second part is that how to so what's the pattern, right? So what's the mathematical structure behind this functional relations? I think this so this generated by the computer, like only probably this is not even this page is not complete. It's not the complete formula. So you have to go back to the paper just to grab the complete formula. I think the best way, so at this, or you can download there is probably a mathematical notebook file like on this archive attached to this to the paper. So okay, so that's my motivation. Here I'm not saying anything. So that's my motivation. So I will just provide some. I want to develop some tools to potentially to achieve some more simplifications or some cancellations behind the computation. So any questions so far? So
in this formula, I cannot find an equality sign.
Yes,
but it's a relation.
Yes, exactly. This is not yet the complete. It's only part of the formula. Like probably I need another page. I didn't take the screenshot. So yes, this is not the
yeah. Let me add one fact, which is that so I mean I was collaborating with Farzad when he found that, and then he asked the computer. Okay, first one had abstractly the formulas which had to be true with finite differences. But then Farzad asked the computer to check whether it's true or not. And when the computer checked it, I mean, Farzad did several times the round of EHES because he was so pleased with with this fact. I mean, so but it's true that it's at the limit of what one can somehow understand. And I mean, this is what Yang Liu is doing actually. I mean,
yes.
So abstractly one can sort of prove the formula. Then to make sure that there is no mistake in any of the computation, you check the formula with the computer. That can be done. I mean, this is not difficult for the computer, but it's obvious that one does not really understand what is going on. I mean,
Yes.
So and this is the task that Yang Liu is undertaking.
Yes, I think. Yes, so I think this amazing fact is that probably like only me and Farzad like really carried out this computation. I think this it's like you have this really lengthy formula, like when you really plug in the relations and then you click the simplified in mathematical and then it's zero. So that's really challenging. But so what you have to like do all this to really appreciate this cancellation, I think. Yes. Okay, so yes, so this is sort of a kind of a like a experimental like computation, right? So we have something complicated, some yes, we surely expect some cancellations. So okay, so let me talk about something like some conceptual, like to see why we're gonna have this cancellation in here. So okay, so here here is the more precise definition of this rearrangement operators. So how do I explain? So given your function, so as before I explained, you take those k and h and t, they are polynomials, right? So then we can extend this functional calculus to a larger class of functions. So they can be like, for example, this can be done by choosing Schwarz functions. So you take a Schwarz functions, take a Schwarz function f. So you can, so by taking Schwarz function, I want to write it as a Fourier transform. So at this stage, you can view this as first of all, you can view this as a formal variables, h0 to hn. So right, this is the Fourier transform. And then this means that then you can really plug in h0 and hn. They are basically, you see that the multiplication operators. So what's the domain of the action of this operator? So it's a for each function, you can sort of quantize this function to a operator to a linear operator from a tensor n plus 1 times to a. So in here, so it acts on elements like rho 1 and tensor rho n in an. So this index 0 and n just label the kind of the slots. Here 0 is the very left slot, n is the very right slot, and the 1 and n to n minus 1 they are in the middle, right? So Yes, so this orange part tells you that how does this operator really acts on these elementary tensors, right? And then you basically from this n-fold tensor to A, you apply this multiplication in here. So here, so usually when you talk about functional calculus, so you expect this to be a algebra map, right? But here we should be more careful. The result is a map from this n-fold tensor to A. So it's not a linear map like from A to A. So like when you do compositions, it has to be careful. So here I just say this is a linear map. So at this stage, I only need this to be a linear map. And probably something like opera will be the right language to handle this issue, but I will not get into that. So I'm going to use two notations to denote this operator. So this as this quantization of f, or these notations. I think this notation is kind of longer, but it has the advantage that you're going to apply transformations on this f, this h0 and hn will reflect. So how do we manipulate all these arguments? So
just a silly question with subscript h. That's of course related to this h0, h0 to hn, right?
Can you? The h is something fixed, like the conformal factor as before. So h0 is so, for example, h0 is the multiplication from the left. h1 is the multiplication from the right. Right, when you're acting on like row 1, something like that.
Yeah, but I'm wondering what's the relationship between all these h's, h0 to hn, and with h, because somehow I understand that you fix your h, it's an element of your algebra A.
Yeah.
And how do you generate all these h0s to hn out of h?
So I think they are. So they are, when you do like we have elements in the algebra, when you do represent, they are kind of derived from h. It's like either as an operator is multiplied from the left or right, right? They're different. Like you have, or like there are different representations of h. Right, like a left representation and a right representation. For example, like you consider group, you can have left regular representation, right regular representation, something like h multiplied from the left or right. Does it make sense? They commute, I think, in this sort of.
The last equation on your slide kind of defines hj, right?
Yes. So from this action, you see that this 0 corresponds to 0 here. They multiply from the left, right? And this 1 and this. So yes, I mean you can kind of ignore this integration, right? So it's a summation, whatever. So you the algebraic notations concerns in here, like how does this so you have a one fixed h, but when considered actions, right? So acting on, so yes, basically how does h act on this? So you have n+1 options, multiply from the left, multiply from the right, and other slots. So that's the.
Okay. Now I understand. Okay. Thank you. Yep.
Yes.
Okay. Thanks. Yep.
Yes. So here's another remark about this rearrangement operator. So I will call this. So I think the essence of this operator, right, is fully captured by whatever underlying function f. I will call this like a symbol of this rearrangement operators. It's like when you often write like a p of d, right? D is a differential like operator, right? P is a polynomial, it makes sense. So, and then what's important is this polynomial function p. So it's a similar thing here. I think it's easier just to call f as the symbol of the underlying rearrangement operator. So I think so. For example, another question is that so of course you can make sense of this sort of a rearrangement for a larger class of functions f, and then for maybe some larger class of operators H. Here I choose a self-adjoint, so like bounded operator. So I think for example, you can consider H to be the Dirac operator, then unbounded. So, and then I think something, and then there's so this sort of a rearrangement process has also appears in another literature like perturbation theory. So I recommend, I think they call it multiple operator integrals. So here is a standard monograph or textbook. So you can find all the reference for this multiple operator integrals. And I think so. Yes, there is an interesting paper of Tien and Waters. So they studied this asymptotics arising in spectral actions. So, and they also make connections with cyclic theory. I think it would be interesting to see how these two stories like can be merged together. So, okay, so this is a remark. So, okay, so now, let me get into this this sort of this variational computation in here. So first of all, I will define so concerning the differential calculus. So I will sort of describe. So based on some basic operations we needed this in the differential calculus. I'm going to introduce some transformations on these symbols. First of all, so let's consider variation. So this is some abstract setup for this variation. So we have a notion of derivation, right? So for given derivation, it has a associated one parameter group of these automorphisms. So we can extend these derivations to the rearrangement operators in the following way, right? So we apply alpha t on H, then we have a family of H, right? And then we can consider differentiation in T, right? So that's the sort of a variational problems I'm concerning here. So, and then you ask, so what's the variation of these rearrangement operators, right? So that's so the formula in here. So it's and then then following the basic calculus. So we can, it's like differentiate in T, right? So it's like, how do you differentiate a multi-variable function? So I think this, so the formula here, I think
it's C-spec.
Sorry. Thank you for good. So the C-spec, I denote by C-spec all these collection of the symbols. It's like all such functions such that this S of F makes sense.
Okay, thank you.
Yeah. So this N labeled the number of the number of the arguments here. I will this x0, x1 until xn. I think it's okay. So this formula looks like you see that we have like a df is equal to like a partial fi fxi, so dxi, right? So in calculus we have this differential of one form, right? So I think it's in a similar spirit in here. So this partial derivatives becomes this phase maps. So I think for experts in cyclic theory, I think so the meaning of a phase map is clear. So I think it's much better. I give you an example. Let me clear this. So give you an example of this. Move it slowly down in here. So yes, let's take an example. F is a function of three variables, x1 to x0 to x2, right? So this will act on row 1 tensor row 2, right? So then you consider this variation, like you compute the derivative in T, right? So and then this is so this J, this label J, so will indicate the position of label this position of multiplication, like from the left, in the middle, and from the right, right? And then the crossword 1, 0, 1, 2. So that's how this operator acting on a tensor, row 1, row elementary tensor like that. Is that clear? This so I think the crucial point here is that this phase map like increase the number of this argument by 1. So and then make use of the the standard Duhamel arguments. I quickly explained before, so we can figure out what's the explicit formula for this phase maps. So here is the explicit formula. So it's like so here dot means that I fix the rest and I take this because f is a multivariable function, right? So I fix one, so view this as function, and then I do this divided difference in here. So and then what's more important, so we have to shift this label like after j. So here is the j. So it's like so you applied the divided difference onto the j's variable of your f, and then some shift of the index. So this proof can be found in a Lash paper, but I think it can be derived as a simple computation using this Duhamel argument, right? So because this f is defined by Fourier transform, basically you have to figure out what happens for exponential functions and then doing some integration. So that's a sort of a standard calculus. So
sorry, but I'm again confused.
Yeah.
So here you are taking out actually both j and j plus 1, right?
No, I'm taking out j. I'm taking out the j spot.
So why is it j plus 1, not j plus 2, not j plus 1?
So because you start thanks for the question. So we start with a function of m plus 1 arguments, right?
Yes.
And then the output is a function of m plus 2 arguments. Okay. So that's why I need this shift of this index. So I can right. So it's like you make this spot like originally it was 1 argument, but with this divided difference you can insert 2. So after this j plus 1, right? Probably I can write as here like a j plus 1, and then you see why we have a j.
Okay, okay, this would have been much more clear. Okay, thank you so much. Yes, yes.
Yeah, I think this. Yeah, thanks for the suggestion.
Yeah. Notation. Just question of notation. Yes, of course.
Yeah, I think it's very important about these notations. So because the right notation gives you lots of simplifications.
Okay, thank you.
Yeah. So okay, so I just explained like how do you do derivatives, right? So and there is another scenario which is much easier than differentiation. So I call this a degeneracy maps. So for example, you have a expression like that. You can think of row 1 and row n. They are the derivative of your h of a Weyl factor. So and then this with a rearrangement. So the simple question is that what if this some of this row j, right? It commutes with everything. For example, I take row j to be 1, so it commutes everything. Then I can sort of factor it out, right? So I do have some simplification. So in this case, what's this? So I can just move this, throw it out to the right or to the left, whichever I want. So then what's the corresponding transformation in here? The transformation is, so once I throw this out, so then I can reduce the number of arguments of f by 1, right? So and then the transformations is simply like restricted to the hyperplane. Like you have a Rn plus 1 onto Rn, like right? Or like a simple point, or a simple observation, like if x, so you have h of j, some row, like a h of a j plus 1, right? What if this row is equal to 1? And then it means that if I move this and then j position and the j plus 1 position, they're the same, right? So if I can move this, or I simply take the row to be 1, right? Then these two multiplications will be equal in this scenario. So then that you set them equal, like at the level of functions. So geometrically is kind of a restriction onto a hyperplane. So which is also mentioned in the Kohn and Fazar's paper. So this so this is one simplification. So any questions about this okay, so another basic operation. So now comes into the core of this the cyclic operator. So this I think cyclic theory I think it's always attached to the differential, some kind of the differential calculus, right? So I mean from simplicial to cyclic, I think it's like the difference. I think the simplicial will catch up all these differential calculus, but the cyclic comes in when you have a notion of this integration. So to introduce this cyclic operator, then I will need a tracial functional on this algebra. So and then the tracial functional allows somehow, so you take the multiplication like this, right? It allows to move this to some factor like in the very front, right? So now with this tracial like integration of like phi 0, so look at what's inside. So if without phi 0 there is not much to be done, right? So you cannot do anything. But so now when you integrate whatever this differential expression inside, so you can try to move the last one to the very left. So and then this gives you some simplifications about this rearrangement. I can say this so I can move all this multiplication of h from the very right to the very first. So as a result, I can get a sort of reduce the number of arguments of f by 1, right? So it's not hard to work out what's the explicit transformations here. So it's some elementary computation, I think. So why do I call this an actual degeneracy? So probably I will explain this in the next page. So I will clear. So okay, so another manipulation so I can do is with the presence of this phi 0 is that so now with phi 0 I can have, first of all, I can have some simplification, right? So I can move all these rearrangement operators on the first n factors. So and then I want to do some cyclic permutation about all these arguments. In this case I want to move this row 1, just I do it here is simply a cyclic permutation, right? I move the row 1 in here and the row in here. It's just so one can check that the degeneracy has this simple relation. So why this called the actual degeneracy? Because a crucial feature of this cyclic category compared to simplicial, so is that it is self-dual. So you have a natural functor from C delta of C to its opposite. So and then I think that the functor so described in I think in Rodet's book. So the first step to construct this functor is to introduce a actual degeneracy. I think that's exactly this one. So this actual degeneracy, I think. So okay, so any questions so far? Clear. So basically, I think I just reviewed some basic operations. I think when you're doing this sort of a differential calculus, right? How to take derivative, how to do integration by parts. I think this, I mean, this cyclic permutations it's an somehow abstract version of integration by parts. So, okay. So okay. So let me summarize. So all this all the new notations. So now I have a sort of a category. So first of all, the objects, they are the collections of symbols where those spectral functions, right, behind these rearrangement operators. So this n label the number of arguments, the number of variables. So these are the transfer, all these some transformations on symbols. So corresponds to some basic steps in the differential calculus. This is cyclic permutation, and this phase maps corresponds to the differentiation. The degeneracy maps corresponds to some when you have something like a rho I equals to 1. So you have a collection of the generators of these morphisms of C. So and then so to complete so we need one more phase map from the according to the cyclic theory. So we have one more phase map defined by, so which at this stage is not seen in this differential calculus, but we know what it is because the axioms of this cyclic theory tells us how to define the one more phase map here. So here the main result is that because I just because all these transformations, they are kind of elementary, right? So it's so you're doing divided difference, or like you restrict your function to a hyperplane. So and then you can just verify that so they fulfill most of the relations in Kant's cyclic category. So that's the first part. So you have this simplicial relation and a co-simplicial, so corresponds to the phase maps and the degeneracy map. So this part is true. It's the same as the whatever in the simplicial category or in the cyclic category. So and then the compatibility between the cyclic structure and the simplicial structure, they are still true. So this is so that's why so what is not true is the compatibility among the simplicial and the co-simplicial structures. So you know the green part, the dark green part is that, so they are the axioms which they agree with the standard cyclic theory. So what's modified is colored by this the green orange, sorry. So in a simplicial or in a cyclic theory, so this is simply 1 in this case. This you get the identity. So now this has to be modified. I think the reason is obvious, right? We've seen that once you have this divided difference of this f of x1 and x2, right? And then you take the limits, right? They call the confluence case, you get f prime of say x1. So you take the limit, x2 goes to x1. So in this scenario, then you recover all this all the partial, it includes all the partial derivatives as the morphism of this category C. And then this part shall be basically the Leibniz property for the divided difference. So as we will see in a minute. So any questions so far? So I think this is the main result. So then I will explain something more like some conceptual understanding behind this. So it's like I introduce a bunch of transformations, and then yes, they form they fulfill like most of the axioms in the cyclic category, but except those orange parts. So
the first orange would normally be 1, and the second orange, what would it be?
1. They're both 1 in that.
Both 1. Okay.
Yeah. Okay.
Yeah.
Yeah.
Sorry, one more question. could you restrict like your symbols to like divided differences are they permute all arguments? They are right.
You want me to go back to the some previous?
No,
slide?
not necessarily. But if you would restrict the space of symbols to all symbols that are invariant on their change of arguments, would you then get back the full simplicial structure, or the full
probably? So I
cyclic
can't.
structure?
So probably I will answer your questions in the next slide. So let's see. So okay, so basically, the rigorous proof, right, is to you just to because I to check the left hand side and right hand side because they are explicitly defined. But instead of doing this tedious computation, I would like to give something like some conceptual proof. So by making comparison with this Hopf-Cyclic theory. So yes, so now I would like to specialize to functions of separating variables. Like you have usually n variable functions that they can be written as some product of one variable functions like that. Right. So and then we know that this function of separating variables, they are a dense subset with respect to the smooth Frechet topology.
You mean if you take linear combinations of them?
Yeah. Yes. So yes, basically, so if I check this on such a, I check these relations on such dense subset, it's kind of I proved, right? So then, but because since I'm focusing on these purely algebraic aspects, so I'm not concerning about this so far about this topology. So let's see what's the algebraic aspect of that. So now this first of all this degeneracy maps, like which reduce the number of arguments by one in this is exactly what happens in the Herschel or like in the Cyclic theory for an algebra. Right? So you have a f0 and plus one, you just multiply this fj and fj plus one. And then this cyclic permutation simply cyclic permutes the order the factors. So then it's kind of because it agrees with the usual like Herschel or cyclic theory, right? So and then the simplicial relations follows immediately, right? So now for this divided difference, because it's like so kind of a function of one variables, it becomes a function of two variables, right? It's kind of like co-product, like like in a way. So let me formally write this as a co-product. Okay, so this should be like for most of the functions, right? So this should be like in a infinite sum, like simply I'm making use of this standard Schroeder notation for this co-product. Let's think, because it's an operator like from which increasing the number of arguments by one. So it has some associativity for the co-product. So which is another way to say that this iterated divided difference is symmetric in all its arguments. So you have indeed you have such this algebraic property. I mean, except that this is not a finite sum in general. I think it's, but yes. So, but I think so. Yes, our focus will be only the algebraic aspect. So and then right. So if you use this notation, it's kind of this map will be exactly the map. Like you extend this fj becomes the co-product of fj. So then this is exactly the map I think in the Hopf-Cyclic theory. So I think so that's the so okay, so why then? So what's not surviving in here is that So basically, so because it's another part of the Hopf cyclic, this explain that so this phase map will have will fulfill the axioms for the, I don't know, it's simplicial or co-simplicial, but so one of the simplicial structures. So the simplicial part about delta is checked because it's already checked in the Hopf cyclic theory. So I think the main difference here is that so we kind of have a product and a co-product, but they do not compatible in the usual sense for the Hopf algebra. So all this grid, the orange part is that right. So when you take the limits of a divided difference, you get f prime instead of f. You don't have identity. You get f prime, the derivative of f. And then this formula is the following version of this Leibniz property of the divided difference. So yes, I think so. The failure of the cyclic structure comes in here, right? So this compatibility is replaced by something like this, some Leibniz property of the dividing difference. I think.
And what's the difference between black triangle and white triangle?
So the same. Thank you. the same. So, yes. Thank you. Okay. So any questions so far? I think this yes, this is a so it's kind of a yes. We have a sort of some potentially Hopf cyclic, but yes, I so would like to ask Alan and other experts in algebra in this in algebraic topology or something like. Is there like a tools in homological algebra somehow to handle this such a situation in here? Maybe there is some nice like homology or cohomological theory behind this, I think. So how much time do I have? So
you have 13 minutes.
Okay, yes. So okay, so good. So okay, so the last part is about applications. So I will, so since it's very late, but I'll still try to do some computation. I just make it not that heavy, some light, hopefully some light computations. So here is the improved version of the functional relation of Commons curvature, and I showed before. So there are the main part is the 3-term relations can be written as this you making use of this the transformations we introduced before. It's like yes, this is a new way to rewrite this relation. So I think the new like interpretation is that there is some actual the phase maps introduced. So this delta 2, so cannot be seen in this differentiation. It's this delta 2 is this one in here, the one more phase map. That's why I'm saying we have to introduce one more phase map by making use of this cyclic operator tau with the. So here is sort of a new interpretation of the Commons curvature's functional relations in terms of sort of this like quasi-cyclic, whatever, this incomplete cyclic theory in here. So another some subtle difference is that so in the literature, like Commons curvature or like the Cohn-Fassas paper, so everything was in the literature, right? So the rearrangement operator is defined in terms of the commutators. So here is the change of variables for the commutators. So once you have this formula, you do this change of variable, and then you can you will recover exactly whatever I showed before. So here, so I think another advantage. Yes, any questions? So I think another advantage of working with these multiplication operators of H instead of the commutator is the following. It's like a, so for example, like when you parameterize the standard simplex delta n. So when you parameterize this, so there are many ways to parameterize. I think that the way you with the most symmetric, so you use this sum of xi is equal to 1, right? So when this xi is so this way you have the most symmetries. Is in particular, it behaves really well with when you want to study the simplicial structure. So I think it's yes. So that's why I think it's much easier to work with multiplication operators to see all this why this simplicial structure holds. I think so. Okay, so here is our computation. So here, so we want to compute the derivative. So now you view this as h of as some function in epsilon, right? So we give h a permutation, some perturbation, like some parameterized by epsilon. I want to take in derivative in epsilon. In particular, so since it's linear, so if I apply this variation on h, you get this a. A is a arbitrary, like other self-adjoint A. So yeah, basically I want to compute the derivative of the following function of h. So the right-hand side has 3 spots where they depend on h. So this is red and orange. So and then when you compute the derivative, so we're gonna apply the standard like a Leibniz property, right? So I will only compute the variation, the derivative of the red part to show some yes. So because it's no net. So to give you a flavor, like once you have this all these transformations, I think there is a really like more algebraic way to implement this differential calculus.
And sorry,
yeah.
T is a 2-argument explicit function.
Oh, so one argument T.
One argument.
Oh, two. Thank you. Two. Like a multiply from the left and the right. Yeah. 2 arguments. Yes. T
and it's
of
very explicit.
Yeah. Something explicit. Yes. Okay. So the derivative of this red part is like you can apply whatever the differential in here, right? So here I compute this factor. So in this line. So you see that so you have a here. I will try to. So you have a here and a here. A because a is equal to delta of a of h, right? So because I want to group the terms like this, I want to move the a to the very right, right? So that therefore a is here. So I want to move a to here so that I only need one cyclic permutation. So if I'm a in here, right, I use one permutation of tau, I move a to here, and then one more tau square, I can move a to the very right. So that's why you have a tau and a tau square in here. So is that then you can compare this the blue part, right? So then the blue part is exactly one of the contributions to the gradient of f. So okay, so far here, this is a standard differential calculus, right? Nothing sort of so the cancellation comes in here. So you have something like this, then you can use the relations between the cyclic structure and the simplicial structure. So this is, you notice that this is tau of this delta 0 is simply delta of 2. So, and then after I one more, so this is so this can be simplified to delta 2 of 1 plus tau. So, and then this is a minus delta 2 of k, which is exactly the very last term of the functional relation in here. So I have to how can I clear my eraser? Sorry, never mind. So let's, okay, so the last application, I want to show you some, so we have a bunch of transformations. So, and there are indeed some interesting functions. So on which this, so when you apply this transformations, it behaves really well. So let's consider this very simple function in here. So this is the resolvent function, right? So it's like you can view x0 as a matrix. This is simply the resolvent functions. So, and then like let's denote by this omega of alpha is just a multiplication of these resolvent functions. But so when I write this as a tensor product, I mean that they have different arguments, right? So, and the index alpha are just simply the exponents on the powers of the resolvent. So and then so let me just quickly go over how does these transformations acting on this family omega alpha. So I think it's it's very simple. So the cyclic tau just cyclically permutes this index alpha 0, alpha n, and this omega lambda is so when you apply the divided difference, it's kind of a group like. So I put a double quote. So there is a minus sign. So probably I should not use group like, but but anyhow, so this is
I mean, but isn't it group like if you change omega lambda to minus omega lambda?
I think it's always there. I think it's kind of tricky, like so. I think it's.
But if you change it to its opposite, because you have the square on the side, so you remove the minus sign in the lower line at least. I mean.
Okay, so I think it's you still have minus, but yes, yes, but anyhow, so I think it behaves like this. So. Mm-hmm. So. And then you can when you write when you iterate all these phase maps, then you get omega of 1 1 1 1 1, right? Like in the following way, right? So it's so I use this arrow means that when you apply any of them, the result is the same. So like if you have 2 copies of omega lambda, then you get a copy of 3. There's an alternating sign in here. So like if you want to reach this omega of 1 like with 4 ones, so then you apply any of them, any of the phase maps, I think. So and then so to get higher power of those alphas, so because the degeneracy map is simply like you multiply, right? So this is omega lambda square. So that's why you have something like 2 in here. So and then you basically increasing the number of arguments, and then you apply the degeneracy, then you can recover all the powers of this alpha. So another I think interesting thing is because since the transformations covers all the partial derivatives and some divided difference, so I can somehow recover some differential relations among all this family of omega alpha. So in here, so let's consider this the simplest case is that we know that when you differentiate omega lambda, you get a omega lambda square minus, right? So we can recover this equation by using these transformations. First of all, I write a partial derivatives as a sigma of 0, delta of 0. And then, so this is the left-hand side, and the right, how to get right-hand side? So you just check, this is for omega to do like omega tensor omega, and then you contract, you multiply, so you get an omega square. So, and then you can go further a little bit. So you can go further a little bit. So, and then you can continue. Oh, I think I missed the, also you can, yes, you can differentiate one more. So then you have a 2 in here. So you can do a similar thing. So you can write the derivatives using this phase and the degeneracy maps, this red part. And then we manipulate the relations between these phase maps. So, and then you see that, so you have 2 terms, in blue, when the blue parts apply on omega, so they both give rise to omega cubed. So you have 2 copies, you have 2. So the left-hand side is the derivatives. I think so one can recover all these differential relations, something like that, right? Some very elementary differential relations from all these transformations. So I think I think so in this way, I think so I can recover some some of the differential relations among this hypergeometric family, like by using this similar trick. I think it's so okay. So this should be the last slides of this. So there is one more slide to 30 seconds to wrap up my talk, is to just go over, just review. So this is the abstract of this A4 term computation. So something I would just to enlarge this a little bit. So in here, right? So this is some partial differential systems which involve a natural cyclic group of order 1 through 3, 4. So I think so basically, so this is some new interpretations of this using this category C. Somehow it includes all the partial differential relations, and the cyclic group is exactly the cyclic group in the cyclic category. I think the last remark is that I think that the computation I show here is kind of it has the potential to be implemented in this computer algebra system. I think it's quite like an algebraic, and could be like it seems to be not difficult to use programming. I think it's so I think that will give some ideas to reach the further simplifications of these A4 term computations. Okay, thanks so much for your attention. So I think I'm over. Right.
Okay, thank you so much.
Yeah.
Thank you.
Yep.
Yes. Thank you.
Where is mine? Yes. Okay, now let's start with questions.
Yes. So yes, let me just because I didn't, of course, I didn't follow the details, but when one talks about the divided difference, I mean, this is exactly the quantized differential in the quantized calculus.
Mhm.
And my question is like this. I mean, when you had tried to have the OPF structure, the OPF compatibility, okay, what you had was like a deformation of OPF structure, which is not a OPF structure, like a derivative of OPF structure or something like that.
Yeah. Yes. Let me.
So I think this goes more into the direction of not being OPF, but being like derivative of OPF. And I don't know if this can be put in some, so I don't know.
Yes, I think the difficulty is that
Yeah, so this difficulty here, exactly, where
Yeah.
what you have is either a derivative or a quantized differential, so which is very much of the same kind.
Yes.
So somehow, there is this, but I don't know if this has been investigated. I mean, situation where you don't really have, you know, like things which would be okay if you had automorphisms, but then you differentiate. So I don't know that. I mean,
Yeah, because I think that this algebraic structure F1 and F2, I think it has been fixed because from those degeneracy maps like this, I think this. Yeah. Yes, I think like from this differential calculus, it's kind of like this co-product and the product, they are already like dictated. It's there because
yeah, sure, it's there from the start. But what one has to understand somehow is what structure is behind your relations. I mean, usually, okay, I mean, if they are well, they seem to be very natural. So somehow,
yes,
you know,
I think it's kind of it's like this. This is kind of you cut this cyclic in.
yeah.
But there should be some other piece that's some.
Yeah.
Right, so I'm trying to, if we can fit into another piece into this, there should be.
Right. Yes.
So it's kind of we're missing some, some other piece to connect with it, because I think it's much larger than cyclic because it already includes all.
Yeah, sure. No, but it should be much larger than cyclic. Yes. Yeah. This is what somehow, you know, one should find out. I mean, that there is something which is larger. What are the relations with cyclic and so on? I mean, this seems to be the right standpoint.
Because when you iterate this, we can have all these differential operators.
Yeah, sure. But I mean, this is, for instance, you know, this is how the off algebra of transverse geometry was found. So what you do, you take something which you'd like to satisfy some relation, they are not quite satisfied. So then you iterate and so on, and find out what is the structure behind it. I mean, as long as these things are natural and they are involved in the computations, it's a good thing to do.
Yes, I think there should be some missing part, like a.
To
make it half cyclic, probably like.
Yeah, sure. But I think I must be stressed by the actual political situation, because in one of your slides, instead of seeing rearrangement, I saw rearmament. I mean, can you check that, or am I crazy?
Yes, correct.
I think this is sort of a probably like an auto-correcting, like when you're typing, right? Use auto-correction.
Yes, but I mean, I think you should correct it, because I didn't want to intervene at that time, of course.
Oh, which part? I think.
Well, look for the word rearrangement.
Yeah. Okay, so.
No, it's not.
I'm trying to find.
Close to the beginning.
Yeah. Rearmament, I think it was rearmament. AR. Continue. Put an R after re-R. No, and then go to the next.
Yes, indeed.
Yeah.
Yes. Amazing.
Okay.
So I think this must be your subconscious, which has intervened with you when you were writing. It's like you know, when we say a lapsus, it's a lapsus, but in writing, not in
yes.
in talking.
Or because sometimes I have to switch between like Chinese input and English input. I somehow destroy a letter or something like that.
Yes, I see.
Yes, something like that. Thank you.
Okay.
Yeah, very good. Any other questions?
Yes.
Go ahead.
So thank you for your talk. It was very, very interesting and instructive, because I am working right now with Fedor Sukichev and Dima Zanin on a similar project where we actually trying to compute this. And we have seen like the same cyclic structure, or the spatial structure inside these terms. And I think methods like these can truly help, like make it very easy. So my question is your main theorem on like this spatial structure. Does this hold for which algebras does it hold? Or only for the tutors, non-commutative tutors?
No. It's abstract. Any
abstract.
This is some universal. It's kind of a universal properties behind this sort of a rearrangement process. I think. Yes, I didn't just yeah. I didn't use any special like you have algebra. Probably this you have algebra with a trivial functional, right? That's
Right.
With some derivations. Then
Right.
yes, that's a
Okay, thanks.
yes. And, yeah.
But I think that you didn't answer the previous question by turn. He asked whether these relations can be really satisfied. I mean, this compatibility between phases and degeneracies can be satisfied if you restrict your algebra of functions to some algebra of functions that have some properties like being invariant. You said that you would answer it in some next slides, but I don't think you did.
So yes, what I did, I specialized to those functions of separating variables.
Ah, that's what you meant.
I was asking about symmetric functions. Maybe it's like trivial if you do that, but
well, I think it is compatible for exponential functions like a f is equal to the derivative of f.
no, I mean symmetric in the arguments, like fx x0 and x1. You can interchange x0 and x1.
Yes, but when you take in derivative and then you restrict, right? So you take a divided difference and you restrict, you still have to differentiate the functions, even though the function is symmetric.
Mm-hmm.
So you still have to differentiate the functions.
Yeah. Okay.
Mm-hmm.
Yes,
So I have to.
I think another thing. So I think is this something like a propagator in this Feynman graph setting, like these functions like this, like the powers of this resolvent. So right, so it's like I guess something like a maybe this will acting on like some nice Feynman graphs. But yeah, this part I have to investigate it, but I don't really know. So this, yeah.
Tomek,
yes, there are some very interesting functions like this, when these operators really act on really well. I think that some hybrid geometric functions they are indeed acting very well because like they are obtained by integrating over the like a standard simplex, right? I think the two simplicial structures there should be some relations in there, like in this. That's for some future works, I think.
I'm afraid I have to go. So
okay. See you, Alan. Thank you for coming. Yep.
Hey, Alan.
Tomek, you have your hand raised.
I have a question, maybe one suggestion and one question. The question is about possible structure behind these identities. So let me say first that if you have a simplicial structure, then you can think about these generators as generators of order preserving maps between finite linear orders.
Exactly. Yes.
Is there some analog of this in this situation?
Yes, exactly. So when you look at yes, it's a okay. Yes, exactly. Let me go back to the transformation side. Which one is the different? Oh, here is the differential. So it's a so when you put it, can I? Sorry. When you put this xj and xj plus 1 here, so I think so you can formally view this x0 to xn as the elements, right, in the standard simplicial category. So yes, I think this formula is kind of the dual of one of the phase maps or degeneracy maps, I think. So because this transformations is about how do you map like a x0 to xn plus 1 to x0 to xn plus 2, right? So I think this so if you write it in this way, I think it's exactly dual to those in in this model of the simplicial categories. But when you apply these notations of f and these brackets, it's kind of a when you restrict, when you go back, it's like if you consider only the different, like a simplicial or co-simplicial, it will be okay. But yes, the issue is that when you interact them, then when you restrict, then you are in counter differentiation. I think that's the kind of the situation in here. You don't get one. That's the trouble. Like, if without this sort of these brackets, usually in a simplicial category, you get identity. But yes.
Yeah. So this looks like the story in vertex algebras.
Oh.
So maybe there's some relation. You said that your structure can act on some Feynman graphs.
Yeah, I want to study that.
Maybe yeah. So maybe there's some common structure behind. And could you come back to this page when you had maps from tensor power of A to A?
Okay. Yes, this definition.
Yes. So these linear maps on the right hand side between the tensor power and A itself.
Yeah.
It has some structure. It's a structure of an operand, which is
exactly, operand. I think that's somehow I guess that's the right language.
Yeah. So my question is, what is the operand structure on the left hand side, making this algebra A an algebra over this operand?
Yes, because I only know I just checked the wiki page. That's the opera, because I want to learn this opera language. I think that's a right language to handle this this issue. So yes, I think the opera will be like a potential tool like behind this. So currently it is beyond my expertise. Probably hopefully a few months later or a year later I can learn a few more things.
Okay, but my impression is that since you are using these products, but shuffled with inserting these intermediate factors like h before of the product, h between the first factor and the second factor, and so on and so forth. These are these h0 and hn. So there could be more general operators or elements of this algebra, not a single h, but there could be more than one h.
Yeah, it could be more than one h, no problem. Yeah, it could be more than one h. Yes.
So this is maybe on the tip of an iceberg of some shuffling of elements in the associative product.
Yes, so I think yes, yes, in my concrete examples, I do have examples of multiple like Hij, because here we are only consider conformal geometry, right? So you have only like one parameter h. In general, you can consider a matrix like a Gij or Hij.
Yes, precisely.
So yes, I do have some examples like that. I guess this algebraic property can be extended, but yes, that's that's for future work. I think it's yes, could be like more different Hij as long as they commute. I think it's a yes.
Okay, thank you very much. It was very inspiring.
Thank you.
Anybody else? I don't see any raised hands.
Not of hand.
Richard?
Not of hand, sorry. But I have to think first.
Okay.
Hi, Richard.
Hi.
So while you think, let me ask some questions. So first, maybe Alain was right about this minus. Let me try to write.
He was no.
Okay, so let's keep it.
No, Young's correct.
Okay, good. So
unfortunately, no.
Yeah. Okay. So now let me ask you about your black coproduct. Your black triangle coproduct. Do you
Yeah.
have some kind of a co-unit associated to it, like some evaluation somewhere?
Co-units.
Yeah.
Oh yes, that's probably another trouble. Yes,
Because you have it co-associative, right? I mean, there are many coalgebras that are not coalgebras. So that you don't have compatibility between the product and coproduct, you can live with it.
yeah.
But somehow, if you won't have a coalgebra, I would assume you might have a co-unit somewhere. Although, of course, just like you have non-unital algebras, you might have non-co-unital coalgebras. I'm just asking whether or not you have some natural candidate for a coproduct for this, for a co-unit for this co-associative coproduct.
Yes, probably that's another issue which you have to take differentiation, I think. Yes, thank you. Probably not, I guess. Or probably, yes, just some evaluation, some candidates is some evaluation of F. But yes, since the you're right.
If I could suggest something. Since you have a differentiation in some of these relations, so this means that maybe it's not a co-unit, nothing like a co-unit, because co-unit, if you think about a group and a neutral element and evaluation at this neutral element, which is an archetypical co-unit of some coalgebra, then if the derivative appears, so maybe it will be some distribution. Okay, it's not like delta functional concentrated at the neutral element. Maybe it's some combination of derivatives of this delta.
Yes, indeed. Yes.
Yeah. So maybe this unit would be some distribution.
Yeah. Yes, indeed. Yes, I guess. Yeah, not that obvious. I think so. Yes, it's
not a delta measure, but at the neutral element, but some distribution.
Yes, I agree. So yes, that's another issue. So it's like once you have this differentiation involved, even co-unit is not at a traditional like.
And another remark I have is that even if you fail to have compatibility between the cyclic and between phases and the degeneracies, or if you simply don't have degeneracies, you still have cyclic homology. I remember once we had such a problem that we had a very nice cyclic model, and we had only phases and the cyclic operator, and everything was compatible in the right way, but we had no degeneracies.
Okay.
But you can still compute the homology groups. They still make sense. And then it turned out that in fact, if we change the algebra structure, all of a sudden degeneracies were possible, and we had really full cyclic module with everything, phases, degeneracies, and the cyclic operator. So that occurred to me when you were, because you see, if you would fail to have compatibility between the cyclic operator and something else, well, that's really a different theory. You don't have a cyclic module. But that's something, that's this is extra. I mean, it's nice to have it, and this is, as you pointed it out correctly, is important for having the cyclic duality, which Alain discovered. Yeah, that's definitely important. But this is not important for having homology groups. You can skip degeneracies, just phases and the cyclic operator. I know.
Yes, I think so. Yes, I think probably we can try to develop some homology or cohomology theory.
I mean, you don't have to develop; it exists. I mean, it's.
I don't know any like a available theory I can grab and apply. I think so far I don't know.
There is such a theory.
Yeah.
If you have an operatic interpretation, then with every operand there is related some homology and cohomology theory. So maybe it's quite different from cyclic homology, but if it's a part of some operatic point of view, then this cohomology theory is in the package.
Okay, yes. So it seems like I have to learn operad for sure.
Using some resolutions of some operads, you can form some.
I mean, because I think if we have such a theory, because then it includes all these differential equations that will be interesting. I think because these relations cover all these differential operators, I guess. So that's.
So this should be some cyclic type theory for some vertex algebras. It's my guess.
Okay, yes. So probably we can, it would be great to find more examples. That's, yeah.
So, Richard, have you thought about your question?
Well, yeah, actually, no, it's not a question. It's an offhand suggestion question. So, divided difference is basically homotopic. It's really homotopic to differentiation, to differential quotient. So you have kind of. So in principle, you have something like a Hopf algebra up to homotopy. So these are H infinite algebras instead of H algebras. But of course, questions, how does this homotopy relate to your multiple operator integrals, right? How does they relate to action? Which is a different story, which I don't have a feeling. But that might be worth thinking of, right? So somehow think of this as being just homotopic to standard Hopf algebra structure.
Yes. Yes, I think. Yes, I think yes. It's a potential way like to find resolutions.
To understand, yeah, right. So these are kind of first order part of a transversal Taylor series or something like this.
Yeah, I think that.
Right.
Yeah, I think. Yeah, yes, I'm looking for some algebraic tools like on that aspect. My knowledge is very limited.
Come on, don't be too modest, please.
Richard, let me show you this calculation. Then tell me where I make a mistake.
Yeah.
So what Yang was saying is that we have
delta omega is minus omega tensor omega, right?
Yeah, I'll write G if you allow me.
So minus G tensor G, right? Yeah.
Right. So now I multiplied by -1 both sides. Delta is of course linear. So I have delta minus G is equal to G tensor G, right?
Yep.
But now this is the same as minus G.
Okay, yes,
G.
you're right. Yeah, sorry, you're right.
Well,
yeah.
It's not me who is right, it's allowance right.
Oh, yeah, correct. It is. So yes, minus G is
group like.
Okay.
So allowance right.
Sorry.
You contradicted allow and you were wrong. Shame on you.
Oh, yes. Oh, yeah.
Okay, I think that's about it for today. If there are no further questions, let us thank Yang again.
Thank you for your patience. I think it's been quite a long time.
But it was fun. It was fun, and basically you ended on time. We just had plenty of questions, which I think is a good sign. So I'll stop recording, and let me remind you that next week it's Richard Nest and quantum group Baum-Cohen conjecture. Until then, all the best. Bye-bye.
Bye-bye. Thank you so much.
Bye-bye.
Bye, guys. Bye.
Bye.